Okay. There's Allison. Hi, Allison.
Hi, Anita. Nice to meet you.
Nice to meet you too. How are
Let me
you
get my
this
kids
morning
on here.
or this
Good.
afternoon or
Yeah,
whatever time zone you're in?
tonight.
Yeah.
Yeah, is evening in Puerto Rico. I'm doing great. It's very, very nice to meet you all.
Nice to meet you. Okay, well, as people keep logging in, we might try and make a start. Welcome everybody to the Oh What a Lovely Molecule workshop. This is the second OH themed workshop that well, at least that I've been involved in. My supervisor, Joanne Dawson, started this like, oh gosh, it was a long time ago now. It's probably what, 7 or 8, was it 7 or 8 years ago? Long time ago, pre-COVID, of course. We had a nice in-person meeting, and that was really productive and really successful, and it set off a lot of collaborations, got a lot of early career researchers in touch with each other who are all working on OH. So that was kind of the motivation of having this meeting. So I'm really, really happy to see so many people registered and so many people are here. So that's really awesome. Um, so I was thinking that we could start by doing some introductions. I had people send in slides. I don't know if people will panic if I put them on the spot. If I can just pick out some of the people who are here that can introduce themselves. I guess I could go first and set a good example. Let me see if I can share this. Got on the Google Slides and I have to share my screen, and I'm doing all this on my tiny laptop screen. So bear with me. Google Chrome. So if I share that and then find my slide, there's me. Does that keep sharing my? Ah, sweet. Ah, isn't it great when things work the first time?
Looks good to me.
Okay, so for those of you that don't know me, my name's Anita Hafner. I'm from the University of Sydney. My past research interests is all focused on OH. I've been doing stuff with OH for it seems like forever now, but it's been like 10 years. Um, so my PhD was mostly on OH and the diffuse ISM. I made I made some code to process observations of OH in the diffuse, into more diffuse, not like masers or anything, diffuse ISM in the Milky Way. I was focused mostly on observations with Arecibo, which is a lot less relevant these days. But my current work is more on OH maser monitoring. So I have an ongoing observational project with the Park's 64-meter dish to observe high mass star forming regions and mostly mainline ground state OH masers. I'm hoping to move to more theoretical work, and I have this amazing data set, which I have a talk that I'm going to introduce it later in the week, which is on maser monitoring, and I'm really keen to get a PhD student to help me out with that. So if anyone knows anyone, that would be great. Um, that's me. Okay, let me see if I can pick on anyone else. How about the other organizers? I tried to get these alphabeticals, so let's see if we can find Michael.
I'm right at the end.
You are right at the end. Okay. I haven't made them all alphabetical yet. Oh, and there we go. You are right at
There we
the
go.
end.
Yes.
Fabulous.
Yeah, so hi everyone, I'm Michael Busch. That's a picture of me way younger with the GPT during grad school. I've been doing OH research ever since grad school, let's see, like 2018-ish, and went to the first one of these, Oh What a Lovely Molecules that Joe Dawson put on. That's where I met Anita and Heap. Um, Yeah, so currently I'm a NSF postdoctoral fellow, University of California, San Diego. I'm moving to NREO Charlottesville in the fall as a Jansky fellow to keep working with OH studies. PhD was at Johns Hopkins working with the late great Ron Allen, Josh Peak, and David Neufeld. So if you know those names, great. Yeah, I've been really interested in like OH and other light molecules that trace this diffuse dark, a CO dark gas. So you can see here this OH signal from Busch 2021, which basically pointed the GBT towards the outer galaxy and found OH emission in every channel where we had H1 emission and no corresponding CO. So that kind of pointed to that there was a lot of this CO dark gas in the outer galaxy. And I've been moving towards looking for this very faint CO dark signal in other galaxies. So in Busch 2024, I did this towards M31 and the outskirts of M31. But I'm also interested in the excitation of OH, trying to get at what TX is, the galactic structure of the CO dark gas on like galactic scales, the H1 to H2 transition, and primarily I'm a GBT user, if you can't already tell. So, but I'm also interested in other telescopes like the Miriam Parkes telescope and VLA and other things. So very interested in like collating the, more resources for us as a community to, what are all the proposal calls, what telescopes can we use to observe OH, and what cool projects can we come up with. So yeah, that's me. And I'll be talking today and I think Wednesday.
Awesome. Thanks, Michael. I might pick on one more organizer, which is Heap. Let me see if I can quickly find you.
Yes, up.
Hey!
Yes. Okay, thanks, Anita. And hi everyone, my name is Van Hiệp Nguyen. I am a postdoc at the Australian National University. I'm working with GasCap team and basically GasCap H1 survey. So I am really interested in interstellar medium across and atomic to molecular gas transition and also the H1 absorption and very new thing, machine learning. So I show here, just read my recent work, the H1 absorption with gas cap survey, and also a few, machine learning models for H1 only. So I worked with Anita and Joe Dawson, my PhD supervisor, before on dark gas in the Milky Way and also some OH absorption lines. And this, this is my photo when I was doing PhD with Anita at Mercury Uni, and yeah, we had a very great time working on OH and CO dark gas in the Milky Way at that time. But now I'm moving basically on H1 only. Yeah, so that's me.
Thanks, Heap. If I could pick one, I think, John, you had a slide, yeah? There we go.
Okay, sure, thanks. I mostly do H1, and I'm really just a spectator at this conference, but thank you all very much in advance for your great talks. I did a little OH back in the late 70s after I'd been doing emission absorption in H1 at Arecibo. We had sort of competition from the Nancy telescope, and they weren't as good as Arecibo at the H1, but they did have a pretty good matchup with the OH emission absorption problem. So this is a paper that I published with the Paris group. And in the many years since then, I think OH has sort of gone up and down in scientific interest, particularly galactic OH. But now, in the last maybe 10 years since the CO dark molecular gas has been discussed in greater detail, OH has become, I'm happy to say, become more in the scientific forefront. So I think you folks are all, as younger people, you're all in a good field. And I think there'll be a lot of good scientific results to come out from this meeting and in the next few years. Thank you.
Thank you, John. Okay, now let me see if I can skip quickly. I see, is it Lucero? Let me see if I can skip to your slide because I spotted you come in. Where is it to you? That's the right one, yeah?
I'm there. Yes.
I have so many windows over windows. I'm panicking. Welcome.
Okay. Okay. Thank you very much for your welcome. Well, I don't know how to start exactly. Maybe talking about the picture that is there. It's back in 2013 when I was a postdoc, and those were my first observations with the Australia Telescope Compact Array. And I also had the opportunity to visit Parkes Observatory in Australia. I was very excited by then. My PhD thesis was about water masers in star-forming regions. And after that, during my postdocs, I started studying evolved stars, mainly post-AGB and planetary nebula that presents maser emission. And I study most water masers, but lately I have been studying OH masers, and I am interested in the magnetic field that they can trace. And well, I am very excited to participate in this conference, and greetings from Mexico. Thank you.
Thank you so much. And next on my list, let me see if I can find Carly. Would you be happy to, where are we?
Oh,
Oh no, I skipped. There.
That's the one. Thank you. Hi, everyone. Good morning or afternoon or evening, wherever you are.
Good night.
Thanks to the organizers for putting this on. My name's Carly Noon. I'm a PhD candidate at the Australian National University up at Mount Stromlo. I've worked with some lovely people here today, but primarily work with Mark Krumholtz and Naomi Milker-Griffiths. We typically are looking at cool and cold gas in the H1 atomic line, but also some CO. So in this first picture here, kind of the middle and second panel are CO components of these big H1 clumps that we see. And this is in the Milky Way nuclear winds. And some of my more recent work is looking at this final plot here, where we're really trying to understand how we can model the different levels of H1 and CO gas that we observe. They're quite unusual levels that we see. We see very faint H1 for the level of CO that we observe, which is not really seen many other places. So we're really trying to understand the evolution of these clouds, how they came to form such a unique chemical composition. And where OH comes into this is we've been doing some of this chemical modeling to try and understand these ratios, and we've brought OH into that after talking to Michael and finding out that OH might be important to these clouds as well. So like John, I'm a kind of observer or taking the back seat for this conference, but really interested to learn and hear your talks.
Thank you, Carly. Okay, let's see who else we have here. Oh no, I've gone too far. Noticed. Tomoya Hirota, are you happy to introduce yourself?
Me? Okay.
Yeah, sorry, I'm just putting people on the spot. I do apologize. Feel free to ignore me if you don't want to. I'll pretend that you've gone to sleep.
So good morning, everyone. I'm Tomoya Hirota from NLJ Japan, and I'm working for the VLBI observations using Vera and East Asian VLBI network (EFN), and also I'm interested in ALMA project. My research interest is for the high mass star formation and masers. And also we are interested in joining SKA in the future. So I'm also interested in low frequency sciences, including SETI. But unfortunately, I have no experience with OH data, so I want to learn many things about OH in this conference. Thank you.
Of course. Thank you for that. And I think, Shinji, I saw you. Oh no. Sorry.
All right, that's me. Yeah, my name is Shinji Horich. I'm based at Tibimbira in ACT, Australian Capital Territory, not far from Mount Stromlo or ANU. And so we are part of NASA, the Deep Space Network, and we have a DSS Deep Space Station 43, which is a 70-meter dish. This is the largest stable dish in Southern Hemisphere. And yeah, so our facility is set up for tracking NASA and international spacecraft, but we are given some fraction of time for radio astronomy. And in fact, our 70-meter dish is most sensitive radio telescope for K-band, 22 gigahertz band. So we observe many water measures and related spectral line around that frequency. And also we've had L-band receivers for ages. And until last decade, we've been observing many for VLBI, typical projects, space VLBI, like Japanese VSOP and Russian radio astronaut. And the previous receiver was only capable for single polarization, LCP. And we recently installed dual polarization wideband receiver. Then, yeah, it has happened earlier this month, and we are still testing. And frequency coverage is between 1.3 and 1.9. We can probably go a little lower than 1.2 band, and which is good for redshifted H1. And last, I showed the example plots. This is a Sagittarius B2 and north. For sorry, it's not easy to see, but I observed this for OH, H1, 4 different OH lines, But this was with previous receiver only for half projections, but we should be able to do much better with new setup, And so so my primary purpose to join this conference is to promote this to more broader communities, and we call for proposal every 6 months. We just passed the previous deadline through ATNF, but next proposal deadline is middle of December. So please contact me if someone is interested in using this 70-meter dish. Thanks.
Thank you very much. Okay, I think we might leave the rest of the introductions to other sessions. We'll just try and do maybe 20 minutes or so of each one at the beginning of each session. So let me stop sharing. So the theme of today, in the first day, is the more diffuse interstellar medium. And in particular, the theme for today's session is mostly about observing the diffuse interstellar medium. Let me see, I've got my windows going everywhere. So our first talk, I'd like to welcome Allison Smith.
Okay, sure. Let me get my talk in front of me and share my screen. Okay, and maybe I'll just quickly introduce myself. I am an assistant professor at the University of Puerto Rico, Mayagüez. I'm in a tenure track in my second year, so I'm a junior faculty member. And before that, I was a postdoc at the Arecibo Observatory from 2020 to 2023 when it closed. And I did most of my work in OH kind of in the beginning of my postdoc and in my PhD. So I'm not working on OH right now, but I would like to do it again. Basically, I would like to pick up on stuff that I was working on in the past and have kind of dropped and been working on other things. And so I will talk a little bit about like my experience today with OH and hopefully get, I'm sure a lot of insights throughout the course of the workshop. And I know there's a lot of junior faculty people here, junior scientists here, kind of early career scientists in graduate school and postdoc stage and so on. So I just wanted to kind of briefly highlight my career path, and maybe that's something that if there's time for everyone to take a little bit of time, I'm sure it's helpful for folks in that stage. But I did my bachelor's in astrophysics at Agnes Scott College and a master's and PhD in physics from the University of Georgia. And then after that, I was basically on the job market for some time. a couple of years looking for a postdoc that I wanted to do. I had applied to Arecibo and really wanted to go to Arecibo since I had done most of my PhD work there. And I got denied for my first postdoc. I was working as an adjunct lecturer after my PhD. And basically, I also had a chance to apply for an assistant professor position that I got to be a finalist for and lost in the end to a person that had 2 postdocs already. So I was finding it kind of very hard to get out of the career stage that I was in. And I decided to try to do research on my own while I was a contract professor. And I wrote a proposal to Arecibo to do one of the projects that I'll talk about today, which was basically look for OH in intermediate velocity molecular cloud candidates. I'll talk about what that is. And it was a proposal that got kind of mixed reviews, but was just rated highly enough to get time. And I said, well, I'm going down there. And I asked my dean for money to take my research students down there. And I went down to Arecibo. And it was there that we spent a couple of weeks, and I had the students observing and got to give a colloquium. And I found out that there would be another postdoc position opening, and that I had a lot of potential overlap with the scientists who were there. And so it was sort of like a mix of luck and also persistence and things like that helped me get to ultimately where I wanted to be, which was at Arecibo for a postdoc. So I just wanted to share that with the early career folks, that it wasn't always like a super easy linear path, but that kind of works out with a mix of things in the end. Okay, and so with that, let me just start. Can you see my screen? Not yet, right? Okay, can you see my slides?
Yes.
Okay, cool, thank you.
Yes.
Right. So I'm going to talk about observing OH in the diffuse ISM, or not, as the case may be, and has been sometimes for me. And so I'd like to talk a little bit about the sort of the motivation for the work that I have done with OH, which is basically to study intermediate velocity molecular clouds. And so this is a type of small molecular cloud in the ISM of our galaxy that there's sort of a small population of these things, sort of like a dozen distinct clouds, or about a few distinct complexes. But they may have an important role in the ISM, particularly if they're more widespread. And so this is sort of what my PhD work was focused on, although I was initially looking for these types of things in CO. And then I sort of transitioned to trying to look for these in OH, which is what I'll talk about. So I'll give a little bit of background about the intermediate velocity clouds, and then I will talk about an Arecibo study that we did on one of the intermediate velocity molecular clouds in OH, and then a survey that I did looking for OH on candidate intermediate velocity molecular clouds, and that's about it. So to introduce the intermediate velocity molecular clouds, first of all, when we talk about diffuse gas, or at least when I talk about it, I'm talking about gas where the extinction is typically less than 1 magnitude. This is according to the Van Dijk and Black classification of 1988. So that's what I mean when I'm talking about diffuse gas. Over here on the right is the Milky Way in CO. Lots of folks might already be familiar with this, but in case not, this was done with a 1.2 meter telescope, actually twin telescopes in the northern and southern hemisphere, one of which is at Harvard. This was led by Tom Dame at the Center for Astrophysics. And what it shows nicely is this is basically the galactic plane stretching horizontally across the image. And this is a mission from CO, the ground state transition of CO at 115 gigahertz, and it shows nicely where is the molecular gas, more dense molecular gas distributed in the galactic plane. And it's kind of what we would expect. You see a lot of interesting structure along the plane. That's where most of it's concentrated, and that's not surprising since that's where all the star formation is and so on in our galaxy. So what I'm interested in mainly is not so much the cool stuff that's going on here in the plane, but in these little pockets that are sort of at high galactic latitudes. So if we're looking at a latitude of 0 in the plane and plus 90 at the northern pole and minus 90 at the southern pole, there's lots of stuff sort of above 30 degrees on either side here that are little pockets of CO. Okay, and these things, there's actually upwards of 300 of these clouds. These are called high latitude molecular clouds. For the most part, they're close to us. In fact, some of them are the closest molecular clouds to us, on the order of like 100 parsecs or so. And in general, they're small, 10 solar masses, 100 solar masses. And studies have shown that rather than sort of collapsing to form stars or having clumps within them that collapse to form stars, they're generally not self-gravitating. Okay, so we don't see star formation in these types of clouds like we do in the GMCs in the disk, even when they are larger, on the larger end of the mass spectrum and so on. And so they may be, in some sense, then kind of excellent laboratories for studying the atomic to molecular transition, which is what I mainly have focused on. And so in addition to the high latitude molecular clouds in general, what I want to focus on for this talk is a subset of the high latitude clouds called intermediate velocity molecular clouds. And these are basically CO emitting clouds, meaning that they have molecular hydrogen column densities on the order of 10 to the 28 per square centimeter or higher, that are shown to be infalling towards the galactic plane with velocities of 20 to 90 kilometers per second. Okay. And so these are not consistent with galactic rotation models. Okay, so it's not a factor of like where they are in the galaxy. It's that these are things that are fairly close to us and are not following galactic rotation models and are infalling towards the plane of 20 to 90 kilometers per second. Above 90 kilometers per second are high velocity clouds. And we also have atomic intermediate velocity clouds. Much of these, there are a few hundred of these also detected. And they also have molecular hydrogen, but it's in absorption, only been detected in absorption, which means the column densities are well below, 10 to the 19, more on the order of 10 to the 17. So these intermediate velocity CO emitting molecular clouds are distinct, okay, from the larger population of atomic intermediate velocity clouds. Okay. And so they're kind of interesting because if we want to understand well, the atomic to molecular transition in general, since these aren't star-forming clouds. If we want to understand how the galaxy accretes gas for star formation, and we have sort of lots of possibilities for where gas could come from high-velocity clouds in the disk, in the halo that interact with the disk, from galactic fountain material, wherein energetic processes in the disk end up kicking material into the lower halo, where it later condenses and falls back down. There are all these sort of possibilities, right, for sort of gas in the lower halo interacting with our disk and affecting the star formation cycle. And so these intermediate velocity molecular clouds are kind of interesting because they're already highly molecularly converted. And so we wonder, did they come from the disk? Did they come from the halo? And somehow some molecular conversion process is happening? And what's kind of the underlying physics driving the evolution of these things? And then, of course, are they widespread? And then if they are, what is their effect on the interstellar medium, on the gas content and metallicity? Okay, so hopefully that motivates a little bit of the interest in intermediate velocity molecular clouds. Okay, and so to kind of introduce them, a couple of the more interesting or more highly studied ones, one by one. There are two clouds in Ursa Major, G135.5 and G135.3, which are shown right here in this figure. This is a dust map of the two of them in the same complex right here. And so these clouds were actually detected by Rico and Hylas, looking for H1 overdensities, basically looking at H1 maps and saying, let's sniff around and see if we see CO in any of these clumps where there's a lot of H1. And so they detected these clouds in that way, and as far as I know, that they were the first detected. G211 plus 63 is over here on the top right, and this cloud was detected looking for infrared excess by Désir, Bazel, and Blitz. People have done a lot of studies on it, and it's one of the more highly studied intermediate velocity molecular clouds, and the only one that we've detected OH in so far, which I'll talk about next. And then down here are three clouds that we found during my master's project with Laura Spagnani at the University of Georgia, where we were basically using the Schlegel, Fink, Viner, and Davis dust maps to look for sort of dense clumps in the infrared excess. In the color, in the infrared excess. And we used that to guide a search for CO emission. And so we found three more. So we sort of like all of a sudden double to 6 of these intermediate velocity molecular clouds. And these things appear to be generally further than the high latitude molecular cloud population in general. And so more on the order of up to a kiloparsec or so. And so there are several distinctions between them and the high latitude molecular clouds, and also between the intermediate velocity atomic clouds. And so we were quite interested in looking for more of them. One of the Rico and Hylas clouds has been studied in several different papers, one of which obtained mass estimates. Okay, so this is the atomic mass on the order of 1,600 solar masses, and the molecular mass on the order of 0.1 solar masses in Benjamin 1996. They also used X-ray shadowing to get a distance to the cloud on the order of 400 parsecs, so this would be one of the closest IVMCs to us. And a later paper in 2013 had a particularly interesting result, because if we're interested in where these clouds come from, then measuring the metallicity is kind of particular importance, because if they come from the disk, we might expect them to have disk-like metallicity. Whereas if they're like the more typical high velocity clouds, for example, in the halo, those are typically low metallicity, right? And so this cloud was found to have like basically 40% solar metallicity. So it was significantly subsolar, which would kind of put these things, if all intermediate velocity molecular clouds are in this, similar category of metallicity, then that would put them in very likely not in a disk origin scenario. So that was a really interesting result. And this is something that hasn't been checked for the other intermediate velocity molecular clouds, and would be really interesting to do. Okay, so this is G211 plus 63. One of the IVMCs that I mentioned has been also heavily studied, and that we've looked at OHN. So it has a velocity of minus 38.7 kilometers per second. You can see a Galfa H1 map. So this is the Galfa data from Arecibo, 3 arc-minute resolution. And down here is the H1 spectrum. And so you can see the local galactic emission around 0 there, and the LSR velocity, and a big peak around minus 40. So the red dotted line is where the CO velocity was, and also the red diamond here is where indicates the peak of the CO emission. And so this is kind of a sort of stereotypical picture, or canonical picture of a molecular cloud in some sense, because it's basically surrounded by a neutral hydrogen envelope, kind of enshrouded in this neutral hydrogen envelope, with the molecular cloud right in the center. And so everything is really kind of observationally consistent with that. And none of the clumps within G211 plus 63 are collapsing to flame stars. We've had like some turbulence studies and also magnetism studies to see if we can investigate sort of the presence of turbulence, or the influence of turbulence of magnetic fields in G211 plus 63. And we started that actually with some OH observations that I'll talk about next. Okay. So these are the first OH observations of one of the IVMCs. This is something that I would like to do for all of them, all of the known IVMCs. We used Arecibo to basically attempt to map G211 plus 63 in OH 18 centimeter emission. And so this is, again, the grayscale dust map here on the background. We basically took a strip across the cloud. All of the circles here that's shown on the dust image are detections, and the 2 X's are non-detections. This took quite a bit of integration to get the detections, on the order of 2 to 3 hours or so for each position. And so the color access here is shown at the top. So the color scale is there. You can see that it's quite low in UV minus V. And we were able to basically, by bootstrapping the for a range of excitation temperatures, we calculated OH column densities and calculated a cloud mass by basically bootstrapping the OH to the EV minus V values and trying to extrapolate a full molecular cloud mass. Okay, and so by doing that, we calculated, sorry for the typo there, that the mass is between about 26 and 820 solar masses for a distance of 1 to 400 parsecs and an excitation temperature between 5 and 10 Kelvin. In any of these cases, the cloud is not gravitationally bound. So we did a variable analysis and determined that the cloud is not gravitationally bound. And you can see down here in the bottom left the OH detections and the, I think in the second position right here. And so it's an interesting looking sort of little double peak there. This is the 1667 megahertz line. We did observe all four ground state CH lines, but I think we only had detections in the 1665 and 1667. So you can see that the RMS is pretty low, better than 10 millikelvin, and it took 2.5 hours of integration time. So that was the first OH detection in an IVMC, and the mass constraint and the virial analysis was mainly what we were after with this first stab, as well as kind of some preliminary assessments of turbulence by looking at the line widths and other properties of the spectral lines. Okay, and so to switch gears a little bit, another project that we worked on with OH, and that I would kind of like to continue, but need to find kind of a different route, is looking for intermediate velocity molecular clouds that are more widespread population. And so one might not really expect that they should be. Maybe they're just kind of unique high latitude clouds or atomic IVCs that are more heavily molecular converted for whatever reason. But in any case, there was a study that was done in 2016, which really kind of motivated looking for more IVMCs even more. And this was a correlation study between the H1 emission and the far infrared emission that was done by Roycer et al. And Jürgen Kerp was his PhD advisor. He was a PhD student of Jürgen Kerp at this time. And they used H1 data from GAS, Bonn, and also Parkes for the Southern Hemisphere. Sorry that I left that off. And they used also the dust data from Planck. They basically took the Planck dust data, used the H1FIR correlation, and said, let's take out all of the dust that's associated with H1 under the assumption that whatever is left over should be associated with molecular hydrogen. And they produced a map for both the northern and southern galactic hemispheres. The northern is shown over here on the right, of basically candidate intermediate velocity molecular clouds. And they had 239 candidates in both hemispheres, and in the northern galactic hemisphere, they had 188. And so they calculate kind of a projected mass of the intermediate velocity molecular clouds that they predict and the known intermediate velocity atomic clouds. And they say that the projected inventory of gas would completely fuel the star formation rate of the Milky Way for a star formation rate of order a couple of solar masses per year. So this is a pretty fascinating and cool result. And so what we were interested in doing is trying to look for some of these intermediate velocity molecular clouds. Since we're looking at diffuse gas, CO doesn't necessarily seem the best route. It's also not easy to get time, for extensive observations with telescopes that can observe CO. And so we thought, why don't we try to do this with Arecibo? And so this was what that main project was that I said that I wrote to get my, try to get myself into a more research trajectory as a postdoc, was to basically go to Arecibo and use the telescope to look for OH emission from intermediate velocity molecular cloud candidates. So there were 42 candidates within the Arecibo declination range of the 188. And ultimately we got initially 63 hours. And with those 63 hours, we looked at 22 sight lines in 11 different cloud candidates from the list. So we used the L-band wide receiver at Arecibo to look at the the hyperfine OH lines at 18 centimeters, and also, of course, simultaneously the H1 line. This is using the wideband Arecibo pulsar processor backend and the sufficient, bandwidth and spectral resolution there. So the map over here is from the Roycer et al. Paper. It basically shows the molecular hydrogen column density, yeah, so this is basically blue shifted and red shifted gas. And you can see that sort of you probably can't see, but the sort of medium blue color and the medium red color are of order 10 to the 20 per square centimeter for the H2 column density. And so the contours here are denoting sort of or actually, I guess the red targets there are denoting the intermediate velocity molecular cloud candidates. and the known ones are shown, for example, as green diamonds. There's a lot of actually things shown in this map, but the main thing that I wanted to take home was basically how many candidates they found. Okay. And so, what we found actually was pretty much nothing. We didn't have a single OH detection. So we had H1 detected, of course, in every position. Intermediate velocity H1 in every position, as predicted. But we did not find any OH emission. When I say no OH emission, I mean like what I showed on here at the bottom right. So this is kind of bad on me because the horizontal axes here are a little bit different. But what you should see is the H1 spectrum here at the top with the Gaussian decomposition overplotted on it. But the intermediate velocity H1 line for this cloud in the survey is right around -50. And down here, you can see the 1667 megahertz spectrum. And down here, right around -53 is where it's supposed to be. You can see there's not even a hint of an OH line. And this is, you can see also how low is the RMS, much lower than even 10 millikelvin. In some cases, we even reach of order a couple of millikelvin in the RMS. So these are quite long integrations. And we did not have a single hint of an OH line. And so in any of the OH transitions. And so what to make of that was that first, we thought maybe, well, the H1 FIR correlation maybe could vary in the diffuse regime of the ISM. But one likely explanation, which has been kind of, I guess, motivates possibly some additional work, is the idea that maybe the molecular substructures, in particular in these intermediate velocity molecular clouds of an even more diffuse nature, are particularly clumpy and small. And perhaps the OH isn't even widely extended throughout them. And with Arecibo, we would have had of order, a couple of arc minutes in beam size. And so perhaps that was too big, basically. And so the other problem, of course, is that the excitation temperature of OH and the environmental conditions of these regions of the ISM were such that it was too close to the background and that we should be looking for it in absorption instead. That would be great. And why didn't we do that to begin with? The thing is that these clouds are kind of small and there aren't that many bright background sources. And so it's not the easiest study to do that way to get a lot of candidates to look for it. And we did check that. But it can be done, I'm sure, for some of the sources, and it could be done also if I looked at more southern sources, which I didn't. And so that's still a possibility to try to do, and I think one that would be worthwhile. So what we did do then was try to put upper limits on the molecular hydrogen column densities to compare it to the predicted column densities that they had in the H1FIR paper. And to compare it to the astrochemical models of Neufeld and Wolfire 2016. And so we used Galfa H1 data, we used Hi4Pi data for sources that we didn't have Galfa H1 data for. For example, when we wanted to compare it to the known IVMCs, we continued using the Slagle, Finkbeiner, and Davis dust maps, and also CO observations from the literature. Okay. And so we, as I mentioned, estimated the NH2 for the known IVMCs, and we found that it compares well with the Reusser et al. Predictions. But for the target sources or for the candidate IVMCs, we actually found that they were an order of magnitude lower than predicted. So I'll talk a little bit about what that is in just a second, which comes down to the clumpiness thing. We were able to constrain with the models the volume density based on NH1 and AV. For the non-IVMCs, it's between 15 and 250 particles per cubic centimeter, and about 25 for the candidate IVMCs. That doesn't want to change. Okay. Okay. And so over on the right, I will explain what I mean by maybe the molecular substructures are too clumpy for us to detect them with a bigger beam. So the non-IVMCs are shown over here on the right, and this is in the parameter space of the H1 column density and what we call the IVAV, which is basically what we try to do to scale the emission to only intermediate velocity emission. And so the candidate IVMCs are shown with stars, and the known IVMCs are shown with circles. And the solid lines represent the model, the Neufeld and Wolfire models, for the NH1 versus AV for a range of different densities here. And so you can see what I mean by the density constraints being between 25 and 250. You can also see kind of the parameter space that we're probing here. So in terms of the intermediate velocity extinction, right, the known IVMCs are kind of down here between 0.1 and 0.2. And the candidate IVMCs are just at the threshold, sort of right below that. And so one would have expected, or I did, one being me, expected kind of some, of course, variety of conditions and so on that might have led to probably not frequent detections, but some detections, nevertheless. So let's see here. Down here on the bottom right is the parameter space of CO versus AV. And you can see here the difference in the density predictions from the model, or the densities from the models. So these are only the known IVMCs because these are the ones that we have CO data for. And the model then puts these between 250 and 4,000 particles per cubic centimeter. And so that's probably because the data for the CO, of course, is much higher resolution than it is for the H1. And having of order arc minute resolution is just of utmost importance to be able to detect this, even with the 3 arc minute Galpa data, and certainly with the 16 arc minute HyperPi data. So higher resolution is probably needed to really be able to do what we wanted to do in the first place. Down here in the bottom left is the molecular hydrogen column densities from the Reusser et al. Predictions, which are shown with the yellow stars. Okay, this work, meaning that these are calculated with the dust emission and the H1 emission. Okay, so we calculated that using the known relationship between the H1 dust and H2. And then the green triangles are the upper limits from the OH observations using an XOH conversion factor of 10 to the minus 7. And so basically our NH2 is of course significantly lower than what some of the Reusser values estimated, which you can see my cursor up here. The Reusser values of the yellow stars on the right of the candidate IVMCs are significantly higher than the green triangles, right? And so probably this is coming down to, or it could be, one thing that could explain it is that higher resolution was needed to detect the molecular substructure. So I think all three of these are kind of consistent with that, but they're certainly not conclusive. But I think in terms of warranting follow-up, maybe they warrant follow-up. So down here on the bottom of this is basically a CO map of the cloud G211 plus 63. Okay, the same cloud that we did the only IVMC we've done the OH observations for. And you can see in the contours here, this is the integrated CO, how big it is. So this is basically, clearly a, arc minute scale resolution is really required even for G211 plus 63. And so maybe in the case of the candidate IVMCs, that could be even more crucial. So future ideas are certainly to try to look in absorption for OH still among the candidate IVMCs that can be searched with bright enough background sources. This is one thing that I think would be interesting in this discussion about telescopes that could be used. It's one thing that I would really like to think about is what possible telescopes could I use for this? And if anyone else is interested in this. Sorry for the noise. Okay. We could have, of course, continue trying to observe in other tracers. CO in some cases may be successful, but we, are all pretty convinced that probably we should be using something else, especially in this regime of the ISM. And maybe, and this is something I haven't looked into yet, is whether we can use the existing PDR models to help us kind of better predict which of the candidate sources we should be searching. So we had previously prioritized that based on the predicted NH2 from the Reusser paper and also the dust measurements had available. And so maybe that's something that we could better target our target list in future searches. And then finally, also, it's not necessarily directly related to observing more with OH, but metallicities of the other IVMCs is also of crucial importance. Okay, I did have a couple of other OH projects. I won't spend time talking about them. I don't want to take up too much time, but I'm happy to talk more about them later on. During my PhD, I also tried to do some magnetic field measurements in a couple of the high latitude molecular clouds and in the intermediate velocity molecular cloud G211 plus 63. I worked on this with Tim Robichaud, Carl Hylas, and Loris Magnani, my PhD advisor. We haven't finished this. This was basically an unfinished chapter of my thesis with some very early preliminary results. And I haven't actually analyzed the OH data from these observations yet. So there could be more high latitude OH detections that we haven't worked on yet. And if anyone is interested in that, I would be more than happy to talk about it. And also one opportunity that we did have to detect some OH, which was encouraging after the the candidate IVMC search, was when Comet Neowise passed into the declination range of Arecibo. We couldn't really lose the opportunity to try and look at it. And so in less than half an hour, about 20 minutes or so, we had a couple of whopping OH lines. And so we wrote that up and got to do a cool study on the comet, which OH is common in comets, and it's been observed many times at Arecibo by Amy Lovell, Ellen Howell, and others. And it basically comes from sublimated water getting, basically photodissociated by the sun as the comet's coming closer. And we were able to calculate a column density and also a couple of other parameters about the comet. And that was a pretty cool study. So I just wanted to end on a positive note. And there's the references, and I'll be happy to talk more about it now or later in the discussion.
Thank you very much for that, Allison. That was really cool. Do we have any specific clarification questions for Allison? Because what I was thinking of with these sessions is that we have a couple of talks back to back to then spur on more in-depth discussion. But if there's anything that we'd like to clarify while we still have Allison's slides up here, does anyone have any questions?
I'm also happy to post them in the Slack at the top.
Oh yes, thanks, Allison. Very nice talk. And I have a few questions. You said that H1 and far infrared coloration would vary in the diffuse ISM. Could you please elaborate a little bit about that? And
sure.
then
Yeah. Mm-hmm.
And then the second one is say that the OH could be very clumpy, and I would like to ask about the physical scale potential or the linear scales for the clumpy structure.
That's a good question. Okay, thank you.
Thanks.
So I may, is that the last one?
Yeah, maybe more about later.
Okay, sure, yeah, okay. Okay, so for now, and maybe we could talk more about this later also, as you said, and I may have to come back to you on the physical scales because it's not really fresh in my mind. Probably we probably talk about it in the draft and in the paper, and I'm happy to check that. The other thing is that you asked about was what I said about possibly the H1 FIR correlation varying in the diffuse regime. This was basically one of the first considerations that maybe it wasn't necessarily a clear conclusion or anything like that from the study, but it was one of the first possibilities that came to mind when we were trying to think of why could the upper limits that we put be basically so different from what the paper had predicted. And since it was using an empirical relationship, maybe in the more diffuse region of the ISM, we thought that maybe that relationship wasn't as robust as it is for other regimes in the ISM. So that was just sort of a first consideration, but I don't think that there's anything that clearly we hadn't clearly concluded that or anything like that.
Yes, thanks. So here you said like H1 and far infrared, like the flux, the correlation between the flux. or something else?
Yes, the H1. Well, basically, I guess it's the H1 column density and the far infrared emission. I can give you the paper I think that this comes from is the Boulanger 1996.
Yeah.
And so that's the relationship that they used, I believe.
Yeah. Okay. Thanks, Alice.
And just so I can't see the sorry, I can't see the. Did it stop sharing? I can't see who was actually asking me the question, so I can follow up later.
Oh, it's
Was it
me.
you?
Yes.
Hi. Okay. Thank you. Sorry, I couldn't see in presenter mode. Okay. Cool. Thank you for the questions.
Yes.
Anyone else? Okay, so if there's any further like clarifications or like really specific questions, we do have a channel for each of our sessions on Slack. So you probably weren't added to. I added you, Allison, to the session one. But if you go to the Slack and you can add channels, and there's some additional channels there. We have one for each session, so we can keep the conversation going there. But before we get into our discussion portion, Michael was going to talk to us about observing with the Green Bank telescope.
Yes, that's correct. Sorry, I'm writing a question for Allison in the Slack before I forget it. Okay, I will. So I think I should share my screen. Okay, move some stuff around. Okay, can everybody see my slides? All right, cool. So,
Yes.
hi everyone. Thanks for coming to this OH conference and listening to some talks about OH. I've been working on observing OH with the Green Bank telescope since, well, I don't know, 2019 or so. And I'll be talking about some recent projects, some older projects, and what observing diffuse OH looks like with a giant single dish telescope. Yeah, so the motivation that comes from using OH, kind of as John and Allison have alluded to, is that we've used CO kind of as our workhorse tracer of molecular gas in the galaxy and the universe. Even telescopes are made for the sole purpose of observing this wonderful molecule because it's so bright. Wasn't the first molecule discovered in space. CH was discovered and then OH, but because of excitation conditions, it wasn't really bright. But the first molecule that we saw that was really bright was CO, and so we made maps of CO, and that's done a really good job at showing us where a lot of the dense gases in the molecular form. And here's the DAME survey that Allison showed. Here's an updated version of it, I believe, with more pointings. I think Tom is probably always observing CO with those two telescopes. But yeah, so some things you can notice immediately. It's very clumpy. If you could look at the velocity axis of this data cube, you notice that a lot of this is towards the inner galaxy. So in the Milky Way in particular, I don't know if this may just be because of where the sun is. It's not our place is not special. We just happen to be at 8 kiloparsecs, where the CO towards the inner galaxy is very bright and CO outside of the solar circle is very faint. And I have some pet theories for why that is. We can discuss that later. So yeah, the dark gas observational mystery was really a thing that popped out of the data when people started to correlate our indirect tracers of gas, so dust and gamma rays, which are proxies for the total gas column, so NH, hydrogen nuclei, with what we were finding from the CO and the H1. So H1, 21 centimeter line, that is a good proxy for the total atomic hydrogen reservoir in the galaxy. People thought that CO would be a good proxy for the total molecular hydrogen reservoir. And when you just plot the two, so on the y-axis, this is dust emission from Planck, and on the x-axis, this is AV, but I relabeled it as NH, which is just NH1 plus 2 NH2 traced by CO, you can see that there's this transition zone where there's excess dust emission. And so, Allison had been speaking about how excess dust emission might point towards, gas in the molecular form. So there is that even when you consider the CO, and this map here made by the Planck collaboration is sort of that component. Now there's a lot of things masked out like the galactic plane just 'cause it's so bright. But yeah, this seems to surround all nearby molecular clouds and seems to bridge the transition between the H1 and the CO. So there's this transition zone that is so far somewhat dark and mysterious to us because we still, other than OH, and OH is very hard to observe, especially mapping. We have pointings, but we don't have maps of this structure with the spectral lines, so we don't really know the phase structure and so on. There are some things we know about this dark gas, and these are just two papers with provocative titles that say it as clearly as some other papers are more diplomatic, I think. But basically, we think we know that the dark gas is not optically thick H1, at least in bulk. So otherwise, maybe we underestimated the H1 content if the H1 is all optically thick. Doesn't seem to be the case, but there's still some people in the literature that argue back and forth about different correction factors for the H1. And mainly that this dark gas is diffuse molecular hydrogen emitted by CO because the formation mechanics of CO, OH itself is a chemical precursor to CO for the oxygen reservoir. The oxygen goes from atomic oxygen to OH and then through some more chemical pathways to CO. And this is a paper by Harvey Liss and Mary von Gruen that basically use HCO plus in absorption, which is a good diffuse gas tracer. Not in emission because its critical density is so high, but in absorption, it is really prevalent in the diffuse interstellar medium. And they said here that just by using the HCO plus abundance ratio, they can recoup this missing molecular hydrogen that the CO is darkened. So these are just two papers I like. There's a wealth of research out there. You can probably look at the references in these papers if you'd like, and find them for yourself. So basically, all that to say is that there's this missing this missing phase of the ISM between the atomic ISM and the dense molecular clouds. We have some clues as to what it is, where it is, but we still need a complete picture. And my dream for the future, I don't know, in 10 years, 20 years, or 30 years, maybe I've left the field by then, but is to have a complete OH map of the sky like Tom Dame has for CO. Then we'll really know, like, oh, okay, this is where it all is and what it's doing. So yeah, there's some still open questions on the CO dark gas. How much dark molecular gas is there? Well, different tracers tend to give different answers, and that is not a huge problem. It's just kind of there's different physics and different abundance ratios that also have uncertainties. And what's the dust to gas ratio? What's this abundance ratio? Are we using the correct excitation temperature assumptions? So some people have their own preferred CO dark gas tracer. C+ is very popular. So where is it? In the sense that we do have these dust maps and gamma ray maps, but we don't have a really good spectral line tracer just mapped out in the general galaxy, and that's because these CO dark gas tracers are very faint, as Allison has shown. And the main question that I think for the science is, how does this affect the Chemical-Schmidt law in the diffuse ISM, where really that law only seems to correlate with H1 now, but if you just add all this diffuse invisible H2 in, what does it say, and how does that kind of evolve? And also, where does chemistry turn on in the diffuse ISM? There's a lot of astrochemical questions you can ask that I've tended to avoid during grad school, but now I'm getting back into. Yeah. So this enterprise of observing 18 centimeter OH with the Green Bank sort of started in 2015 by Ron Allen, who was my PhD advisor, who unfortunately passed away during the COVID pandemic. We spent many years and many summers going to Green Bank, just driving from Baltimore to do surveys and observing with the Green Bank telescope. And these were really blind surveys. I mean, the idea was we just point to a random patch of sky, not towards any particular star forming region, not towards any supernova remnant, because we really wanted to get at what is just the bulk gas doing out there. Not all the ISM is star forming. Most of the ISM is just kind of sitting there. So we'd like to know what it's doing. So that's an idea we had. Just sort of in the background, like how you check calculating OH column densities. What do you need to know? Well, the integral under the line. the background continuum temperature is important just for that contrast with the excitation temperature, which Allison's already said. It's between 5 to 10 Kelvin, but it can get really close to the background temperature. And when you're looking towards the inner galaxy, the background continuum temperature can be much greater than the excitation temperature. So these OH surveys towards the inner galaxy, like with Parkes and the SPLASH survey led by Joe Dawson, that showed like, a very well, first of all, it's very blended, but also showed very interesting profiles that switch from absorption to emissions, hard to interpret. So that's why I like working with the outer galaxy or high latitude sight lines, where it's kind of clear. You just get your one profile, and then okay, I can fit a Gaussian to that. And then once you have your OH column density, you can transform to H2 using a very canonical relation. It's about 110 to the -7, as Allison already said. This is using CH as a proxy for H2, but the Westlack work, I believe, doesn't use CH, so I think that's absorption line spectroscopy of, let's see, some of the far ARI lines of H2. Yeah, so as I said, the outer galaxy is a good place for OH emission surveys, primarily because one, you don't have the kinematic distance ambiguity. So as you just look towards the outer galaxy, just you can imagine this red line or this red dot is the sun, then you cross certain features in your sight line. I've just labeled kind of a random GBT spectrum that is, I mean, we have many of these spectra, but here's one I really like because it's quite nice. So it's a sample 2-hour spectrum. Our baseline is always about 2 hours or about 3 millikelvin RMS, and then I've progressively worked up to 10 hours and 20 hours and 30 hours, just looking for more diffuse things and what we can push the OH to really do. I think about 30 hours is kind of the sweet spot. After that, it gets kind of a lot of observing time, unless you're doing Zeeman work. But yeah, so this is a lot of my early work focusing on these OH surveys towards the outer galaxy. In the outer galaxy, most of the sight lines are CO dark. So this is kind of a typical sight line where you have loads of H1. The OH, just in a 2-hour spectrum, is very has some narrow Gaussian-like features that correspond to potentially spiral arms. Being a little diplomatic there, because there's a lot of people who argue about what is a spiral arm, and maybe the Perseus arm is a Perseus illusion. That's what Josh Peak would say. And Bob Benjamin doesn't think anything's a spiral arm. But anyway, so maybe these are spiral arms. But in the CO, importantly, there's nothing in here. And this is kind of true for about like 70% of all the sight lines that we've observed in the outer galaxy. So that's kind of worrying. We'd like to know, these are both molecules with, in the case of OH, adjusted abundance ratio, which is probably more concrete than the X factor. So yeah, there's a lot of uncertainties between the two, and some open questions. If you plot the OH profile integrals versus the CO profile integrals, this particular plot plotted here is just for all the features, so it includes the local features, also the outer arm features and the Perseus arm features. So kind of get a spread of features here from Allen 2015. And you can basically see there's two regimes. There's one where the OH and the CO correlate with each other. It's probably sightlines where AV is above 1.5 or 2. Then there's loads where it's CO dark and OH bright. And that's probably where we have less volume density, less AV. In 2021, we published this this stacked profile towards the outer galaxy. I believe this was 80 or 100 hours. The details are kind of fuzzy now, of GBT data in the blue line. So the blue line is 8 positions spaced by GBT beam width, around about a L of 105 and a B of 3. And so that's why, especially towards the local velocities, you see there's a bunch of local velocity features. But that's not really the important part. The important part is there's signal in every channel where you have H1. So this kind of shows that you have OH following the H1 distribution towards the outer galaxy. So there's a lot of OH out there in between the spiral arms. And this is the corresponding CO spectra in black. The green line is also an OH spectra with the 20 meter at the Green Bank Observatory, which Ron made us observe with too, and before we published this paper, because he said there's no one's going to believe this unless we have 2 telescopes and two OH lines. So we also have the 1665. So yeah, that was very interesting. I will say we have some potential CH follow-up with the Effelsberg telescope. That's led by Arsha Jacob. And the implications for this is that, well, we also did a longitude survey, and we saw that the OH emission was tracking the terminal velocity of the H1. So our implication there is that, well, okay, this is a disk of extremely diffuse OH. If you take that caveat that this is a beam averaged column density, so that is kind of back to what Allison was talking about with the substructure. There could be lots of substructures to this that's just averaged over the beam. So, but if you just take it at face value, then you'd say this is about 5 to 50, 10 to the -3, or Ron used to say about 5 molecules per liter, which is very diffuse. Okay, so then I've kind of moved on to in my postdoc to, well, a lot of projects, but what I want to talk about is using OH as a tracer for dark molecular gas in other galaxies, which is kind of a standard astronomy thesis, is that you do something in the Milky Way and then just slowly move out of the Milky Way. So this is a GBT pilot survey we did, just kind of like filler time, but we said, okay, we found this very diffuse, very widespread OH signal. Can we find it in M31? And so we looked at 2 pointings, and this is the dust mass surface density. So we're guided kind of by the dust in the H1. So we looked at 2 positions with integration time about 30 hours. Just moved to 4 kilometers a second. So we had RMS about 0.4, and we were beyond the CO ring. So all the CO out here was very faint. And so the answer is yes, we can find this signal. And so this 1667 spectra is shown here with just a single Gaussian fit in blue. And the 1665 signal appears to be in about the 5/9 LTE ratio. So that would argue against this being a bunch of unresolved masers, I would argue. But yeah, the peak signal in OH is about 2.5 millikelvin. And I would say this is not a detection in 1720. That is fine, because if it was 9 times weaker than 1667, then it would be buried in noise. So, although I showed Tim Robichaud this, and he's like, "That's definitely a detection. Look at that." And I'm like, I don't know, but there's some CO here, too. There's some faint CO. As well in the magenta pointing, and the yellow pointing was a non-detection, which I was initially sad about, but then I figured, well, this is a good actual confirmation that there's no instrumental effects that just so happen to make a LTE OH emission signal at the velocity of Andromeda that I'm unaware about. So that was fine. I'm fine with that. But yeah, this is very exciting. Published this in 2024. And if you just use the conversion factors, H1 is H1, but you would just use a standard XCO, then, and two guesses here for the excitation temperature of OH, where the orange one is pretty conservative. That's a TX of about 10. Then conservatively, the OH here traces about twice the H2 mass as traced by the CO. And we looked at the dust surface mass density, and also just took the median surface mass density in that aperture, and we found that this is pretty consistent even with this literature value for the abundance ratio. So there's some uncertainties that you could add in there. You can increase the abundance ratio. You could say it's maybe 10 to the -8 or something, or 10 to the -6, but I think this is kind of okay. It took me a long time to believe this too, but I think this is about right. Yeah, but still, so that was one sightline. So the follow-up is, of course, could we just do some more? So I had written a proposal for the GBT last year, and I had asked for 300 hours, and they said, "We'll give you 170." And I said, "Okay, fine, deal." So I asked for this time to do this OH survey of the CO molecular ring in Andromeda that was finished this spring, actually. So every aperture here has about 10 hours of GBT time observed on it. And so the questions here is that okay, now that we observed a very CO faint position, how do the CO bright arms of M31 compare between CO and OH? And can we find any truly dark CO CO dark spectral components in these red apertures where the CO is very faint or just not there at all? And there's a lot of like HSD data and like dust data that we can use to calibrate the OH to H2 ratio too. So let me show some OH data. So I'd originally asked for 20 hours for pointing, and that was shot down. So I said, okay, we'll do 10 hours per pointing. And what I found was that actually the OH is very bright in this ring, which was very exciting. Even with just 4 or 5 hours, we found loads of OH. which maybe is not a surprise. Karen Sandstrom here at UCSD said, well, I mean, if you point at the CO bright stuff, maybe you just do get more molecules, and that's fair enough. But I was a little more cautious. So here's this first position here, which with about let's see, 4 hours, 4.5 hours of integration time for the OH in 1667. You can see it matches up very well with the H1. And that there are also multiple components. So, you know, the next step is to look at the CO and maybe get the spectra and overplotting these regions here that show more substructure and see, do those components line up with the substructure in CO? And also, are there any CO dark components? That would be really interesting too. We also found 1665 at that position. I haven't checked if they're in the LT ratio, but I suspect that they are. But it would also be interesting if they're not. So here's another position in 1667 with about 4 hours of integration time. And just another one here. And at 0 is, of course, the local Milky Way H1. So that's a project I'm currently working on. I'm very excited about. If you have any ideas of what else to do with this, let me know. And yeah, I mean, I thought it was a okay ask, a very interesting question. I asked for a lot of time and they gave it to me. So, I mean, it's a very a nice science topic, as John said in the start. So I just wanted to spend a little time about observing with the GPT, and I will say up front that I'm blissfully ignoring the current budget situation in the US. So the GPT in the budget is, I think, has a proposed 70% cut. So if that happens, then maybe this just won't be a thing. But if not, and if we're still using the GPT in a year's time, then I'll just say that there's usually an August call and a late January, February call. I believe this past call was January 29th. But I have a lot of experience with observing GPT. If you have a cool idea and want to talk to me, please let me know. The NRAO and the GBO science staff are also very friendly. I put some links here, and I'll of course share my slides. If you want to be trained to use the GPT, usually that occurs during the summer. So in order to do remote observing, you do need to go fly to Green Bank, get trained by an observer, and then you get a little certificate. I don't know where mine is, but you get a little certificate that says you can observe with the Green Bank from wherever. So now I just observe from my laptop wherever I want. Yeah, so I'll just stop with that, and that I would love to gather, you know, more information on telescopes. If people have their favorite telescope that they want to share observing calls, I'm all for that. I would love to put together like a document, maybe in, you know, this in the Slack channel that we can share later with everybody. But I'll just end there. That yes, you could use OH as a potent tracer for CO dark gas. I think we need to, because it's one of the easiest tracers that are still accessible. I mean, we don't have Sophia anymore, so we can't do C+ locally. But there are a lot of radio telescopes, and we kind of piggyback off the 21 centimeter advances, which is nice. So I think OH still has a lot of leg to it. Yeah, okay, I'll stop there and take questions or start the discussion. Yeah, all right, thank you, everyone.
Thanks for that, Michael. Does anyone have any questions for Michael?
Thank you.
Oh, he was super clear. Left nothing for any. Oh, Allison, there you go.
Allison, yes.
I will ask one. I will use to digest because there was a lot of cool stuff, also new cool stuff that I didn't know about. And congratulations on all of that, and also on the Jansky Fellowship. So very happy for you.
Thank you. Yeah.
Can't think of a more deserving, person for that. So very excited for you.
Thank you,
And
Allison.
the question I wanted to ask was about that GBT spectrum of the OH. And the Milky Way, and you had the H1, the CO, and the OH all overlaid because there's that. Yeah, thank you.
Yeah.
Sorry, the OH is in the blue, right? And I just was wondering,
blue
like
and green, yeah.
Blue and green. Okay, I was wondering what to make of like the end of the spectrum on the left, above, further out than minus 120, where the OH is actually above the H1. I was wondering what you attribute that to.
I I think honestly, I would attribute that to a little bit of baseline error. The green one is probably a little bit more correct, because the reason we looked with the 20 meter is because the 100 meter has spectral ripples in the order of 1.4 megahertz, which we thought could have been the cause of this broad signal. When you go to 20 meters, that ripple becomes 9 megahertz, and we fit that very well with the polynomial, and we were convinced this was real. But it's still that ripple's still in the GBT spectrum. So I'm not sure. I would only believe maybe out to like 120. Although I would say it's still plausible. I mean, John Dickey has some recent research on CNM fractions, so cold neutral medium fractions of about 10% out to very far galactic radii. So I'm very interested in following that up with OH, but I don't know if I would believe it just because there's not H1, not a lot of H1 emission out there. There's still some H1 emission out there, but yeah, I don't know. It deserves follow up at least.
I was curious, I mean, just in general, but also because one of the things I am now working on is also CH in the galactic plane. And there are some really wide components of CH. And I was wondering, I mean, also we were being very careful also about the baselines and such. And so I was kind of wondering if that is baseline related and so on. So yeah.
I would think that one probably is slightly baseline related at at the like 1 millikelvin level. Yeah, if you just look at the statistical error, then you'd be like, oh, that's all OH. But I'm a little bit more cautious.
Yeah.
That's why I just present it, and then I also present the 20 meter spectrum.
Right.
Yeah.
Okay. Cool. Thank you.
John?
Yeah, beautiful talk, Michael. Your last comment makes me wonder a little bit. For many years, on the basis of the CO, we have thought of the surface mass density of the molecular phase as being an exponential decline radially in the Milky Way. And I wonder if you would revise that now and say that the molecular surface distribution is a bit more like the H1 and not an exponential.
I would revise that, and something that Ron and I was talking about before you passed is that, well, people think it's exponential, and it's probably more flat, which is kind of shocking and a revision that probably needs to be explored. I do have more data towards the outer galaxy that I haven't looked at, so I mean, it's something I need to look at. I mean, there's loads of data. I think the special call is another 100 hours of outer galaxy data that is a longitudinal survey, and that was just more looking at this terminal velocity stuff. Do the terminal velocities align with the H1? And I think they do, and I think it needs to be revisited. So I would love to chat about that, and I would need help and some expertise to, yeah, to think more about that and how best to pitch that to people in a way that they wouldn't immediately, disbelieve. Let's see. I see multiple hands, but Chikadu, is that right?
Yes, that's me. Thank you, Mike,
Yeah.
for your presentation. I think the early slides, one of the early slides you had, where you tried explaining how to get all those properties from the spectral line. My background is Mesa, so yeah, I would like a little bit of explanation on how to. Yeah, maybe 1, 2, 3. I got your number 4, but no 1, 2, 3. If you can quickly explain those, please.
Yeah, so the one is I should probably label this equation, but one is this integral here, right, where we have the integral under this line, any of these components. So it's an integral of where the units end up to be Kelvin and kilometers per second. So you need the integral under the profile line. Could be in absorption, this would be optical depth. In emission, usually we use Jansky's or antenna temperature. I prefer antenna temperature because it's what a single dish people usually use. And then the excitation temperature. This whole prefactor is more like a background correction factor, where the excitation temperature is, that's just the ratio between the upper and lower state, and the background continuum temperature is usually CMB plus synchrotron radiation at 18 centimeters. And that's important because if your background temperature is more than your excitation temperature, then you get an absorption line. But because we observe that it's emission, we know that Tx has to be bigger than Tc. We don't know by how much, so there's some uncertainty there. It could be 5 to 10 Kelvin, could be even more, could be closer to Tc. And usually that introduces like about a factor of 8 in error, maybe up to 10 or 11, depending on how close Tx gets to Tc. If Tx is much greater than Tc, then this prefactor is just 1, and that is a limit you could use in your analysis. It's helpful, but I'm not sure how useful because it's just kind of ignoring all those uncertainties. Yeah, but this is all the assumptions of like of LTE and stuff. I think that's just swept into this other prefactor of 2.3 10 to the 14, and all this equation has been much more simplified. There's the base equation is from, well, I would use Shirley 2015. I could link that if you'd like.
Yeah. Thank you. Thanks for the explanation.
Yeah. Okay, Van Heep, I don't see anyone else. So
Yes, thanks for a very nice talk, Michael. I like very much your new data from M31. And so I'm curious, within the Milky Way and in the M31, have you had a chance to estimate the abundance ratio of OH in the M31?
Oh, not yet, but that's a very good idea, and I would definitely like to do that radially, I think, probably, but also just for each position. But yeah, I would probably just use the dust for that, and of course there's an assumption you have to use for the dust to gas ratio. But I think the probably Carl Gordon and team and Chris Clark have probably I think have figured that out. So I will rely on them for the uncertainties in the dust to gas ratio. But yeah, they will have to factor that in. But yeah, that's a good idea.
Yeah, I really looking towards for that. And within the circle here, this is the telescope beam size, I guess, the green band.
Yeah, it's about 7.6 arc minutes for the GBT. So it's not spatially resolved, but it is velocity resolved at a high velocity resolution. I think this might be native. Oh no, I've smoothed here to 1 kilometer a second. So, these components might be these blobs here in CO. I'm not sure yet. I need to overplot the CO. Yeah.
Yeah, that's great. See it. Thanks.
Shinji?
Yeah, I'm interested in how you observed for the galactic observations. You averaged 8 points. For each point, did you observe on source continuously, or you needed to switch between off source and on source? Or yeah.
These spectra.
Yeah,
is that what you're talking
this
about?
one. Yes.
Yeah. We use frequency switching for the blue line, and for the green line, we use total power observations, actually. So we didn't use a reference spectrum for that one.
Okay,
We did do a lot of tests, and we determined that the radiometer was stable enough, like the baseline was stable enough. But the green line is a 100-hour stack between 2 different positions spaced by a degree. So it's 50 hours and 50 hours and averaged together. And then the blue line is 8 kind of in a daisy pattern, centered on 105.3. And that was frequency switching. That's why, yeah, there's some baseline things that in the blue line maybe I won't trust. So the precision is a little bit, I think, plus or minus 1 millikelvin, but the mean signal is about 4 to 5 millikelvin. So I trust that it's there. It's just the precision is a little off for the blue line. That's why that stuff at negative 140, I'm like, still cautious about.
So how far did you have to switch frequency, and is there any overhead to do that?
No, we switch frequencies very often. There's very little overhead. You spend most of your time observing, and it's in band frequency switching, so you don't lose the signal at all. We throw the signal about 2 megahertz, and you could see when we were. I don't have any of the. I do have some versions of this talk where I show the raw signal, but I can maybe post it if you're interested in the Slack. Testing of the polynomial fits, but you can see this broad signal appear in the spectrum 6 times, twice in the 6065 and 1667, and then 4 times switched left and right in frequency, but negatives of them. So it's an interesting spectrum even in the raw data. But yeah, it does appear frequency switched, and we were very careful to treat that.
Yeah. Is that one of the standard modes of the GBT? Yeah.
Yeah. Yeah, and since we figured out that the OH is pretty spread out and we don't know where it is, a priori, that position switching is kind of tricky because you might just observe OH accidentally, even if you go high latitude. Yeah. So in position switching would add a lot of observing time if you're doing some, some long integration times.
Yeah. All right, thanks. Yeah.
Yeah. Okay, so I'm gonna stop sharing. I think we can just do discussion now.
Cool.
Does that sound good, Anita?
Thanks for that, Michael. Yeah, so the main discussion point that we had listed for this session was to talk about like who to talk to for observing with different telescopes. So I was madly typing as Michael was mentioning such a lovely suggestion of having of having a list on Slack. I've got a share drive that we've set up for the workshop, and in there I have a list of telescope contacts. I put a link in the Slack for this session, so if you want to join that channel for this session, then you can see I've shared it. I won't share my screen or anything, but I've just put columns there for like the telescope, a brief description of the telescope and maybe the receivers, when the proposals are available, the type of observations that you know how to do and that you've used before, and then just your name and an email. So my hope with that is that so I've just put myself there as the first one to get things kickstarted, because I've used the 64 meter Murray dish at Parks a lot for spectral line observations, mostly for masers, but I've also used it for some diffuse OH. I've also used the ATCA, but that was long enough ago that I don't know if I'm willing to put my name down there for that. But what I was hoping there is that different people who are present, if you have experience with a telescope, like all the way from even proposing, observing, analyzing, whatever part, if you specialize in something and are willing to be a contact, I think that would be a great way for us to promote more wider use of telescopes for OH observations. Because I know if I wanted to observe something that was very faint in the northern hemisphere, my very first step would be to contact Michael and say, hey, help me. To that end, I made a couple slides. I'm not going to share them right now, but I put them again on the share drive. I just make slides because that's my way of formulating my thoughts. But on how to propose to do observations for the AT&F telescope. So that's the Australia Telescope National Facility. We have a whole fleet of radio telescopes if you want to complement your northern hemisphere observations with some southern hemisphere. So that would be Murray dish, the 64 meter dish at Parks. Also the ATCO, which is the Australia Telescope Compact Array. That's a 6-dish movable interferometer. We also have ASCAP, Tidbit-Billa, MOPRA. There's a long baseline array that involves all of those telescopes. I'm sure I'm missing some very key ones. But I happen to be on the time assignment committee for that. So I have a lot of like insider information of how to propose. But if anybody is interested in using any of those telescopes, I think one of the things that might prevent people from doing it is that there's a lot of difficult steps, right? You have to use some online system and everything. But Like if you could write the scientific justification, I'd be happy to write all the technical stuff for you for your observations if you put me on your papers. Sonia, does anybody else feel like they're expert enough in a telescope to put their hand up? Michael already has.
Or if you have ideas of people or telescopes we should reach out to. Yeah. I don't think FAST has their OH receiver up yet, unfortunately. But
my understanding with FAST is that their main receivers can't observe the 1720 line, but they do have a commissioning receiver if you know the right people, which D. Lee would be one of the right people. I don't think he's registered for this meeting because it overlaps with some other stuff. But if you're interested in using FAST, you can send me an email and I could then send D an email. Unless there's anyone else here who's more experienced with that. But I should mention also with the Murraying dish at Parks, we're currently in the process, it seems to be a 5-year process of commissioning a new receiver on the dish, which is the cryopath. So that's a phased array feed that at some point in the future, should have been 3 years ago, at some point in the future, it should be able to do a 72 beam footprint on the sky, which would be really, really nice if you're interested in doing any kind of broader surveys, because it could potentially speed that up. It's being offered in the coming semester, which the deadline just passed for ATNF telescopes. But it's every 6 months there's proposals. I've put in a proposal to use a cryo. I'll let you know if we get any time. But so far there hasn't been any scientific observing on it yet. It's still in the commissioning process. But that'll be a super valuable one because it goes from 700 megahertz to 1900 megahertz. And the noise levels are like, they're pretty good. They haven't been able to test them on the telescope completely working because most of the problems we've been having have actually been with the cryogenics, which is unfortunate. But some of the testing they've been able to do, like sub 30 Kelvin, even down to like 20 Kelvin in some of the tests of the noise levels. So that's pretty good. That's pretty good. So you get the sensitivity of a big, huge 64-meter dish, but also a really low noise floor, if I can speak properly. Hopefully that carries over to when it actually starts working. But who knows? The process of commissioning a new instrument is like, how long is a piece of string? Who knows? My whole postdoc was supposed to be on commissioning this instrument, and it never happened.
Well, yeah. I also submitted a cryopath proposal, so we'll see. I guess they switched from shared risk to not shared risk, so I think they're confident. Yeah, I think phase rate feeds are kind of the future for mapping diffuse OH because it takes a while to observe. I can report that the planned phase rate feed alpaca, which maybe you noticed that logo on my slides, I forgot to take that off, was actually canceled, unfortunately, on Friday. So that was some bad news because of USA budget cuts. It was supposed to go in Arecibo, but then it was supposed to go on GBT, but now it just seems to be not a thing anymore. So, but hopefully cryopath still will work in the future. But yeah.
I did not know that about alpaca, that it was cut. That's pretty devastating because yeah, that was a big hope for many of us.
Yeah, that was
yeah.
devastating to hear. We'll see. I guess the instrument, I mean, it's a receiver that is completely made that just needs to be
exactly
funded and put on a telescope. Yeah.
Speaking of phased array feeds we didn't get to work on, my postdoc at Arecibo was to work on alpaca on Arecibo in 2021, by which point we didn't have it anymore, of course. But yeah, anyway, so I was very much waiting for that to be on the GBT.
It was a major component of my Jansky application.
Yeah,
so
I can imagine.
I feel that pain. Anyway, does anyone have any happier topics? Beth, just because no one's talking, which link? Oh, yes. It's in the Slack. I will put it
It's in
there.
Slack. I don't know if when you join a Slack channel, are you able to see previous messages? No. Or is it, it's like what's okay. I shared it in the chat there.
Oh, I think so. It's session 1 observing diffuse OH. Are you maybe Beth is not a part of the channel?
I'm not sure. I can't see who's in the channel. Hey
I
Beth,
think maybe if you pin it, then people who join will definitely be able to see it.
there you go.
Okay. I've added you, Beth.
Oh,
Okay. And I shared it again just under you being added, so hopefully you can see it. Keep asking. I'm happy to keep sharing.
Yeah.
Something I wanted to mention though while we were on the like while we have Allison here and Michael also who you guys are both doing observations not necessarily in the galactic plane. That's something that's worth mentioning about the AT&F telescopes, particularly Parkes, is that it's relatively undersubscribed for off galactic plane observations. So we have an oversubscription rate of sort of a factor of 1.5 or 2 for Parkes, but that's heavily skewed towards a huge oversubscription rate for galactic plane observations because having been on the time assignment committee, I know that the vast majority of observations that we do are pulsars, and they're mostly in the galactic plane. So if you have a pet cloud or something, especially if it's off the plane, even if you don't get a spectacular score, you're likely to get some time. So that's another thing that's worthwhile mentioning, is that there are telescopes that are not so ridiculously heavily subscribed.
Yeah, thank you for that tip. That is definitely good to know. I have not proposed for Parkes ever, and I would definitely, it's been like on the bucket list for a very long time. So definitely do want to do that at some point. I need to prepare for that and do it, and I will definitely reach out for help about that. But do you know if there's like is there kind of a threshold number of hours for typical standard proposals that's recommendable, like a large proposal versus regular, like a GBT? I'm used to kind of like large proposals, or something being like above 100 hours, less than 100 hours, like do long.
Yeah, we kind of had, there's some very not well-defined categories of whether or not something is a large project or a small project, because there are slightly different proposal pipelines you end up going down. If something is a large project, I believe it's something over like 150 hours or so. I don't know. It seems like that line keeps shifting, and every time I try to find exactly what the requirements are for a large project, I can't find them. So it's a bit fuzzy. But again, having been on the time assignment committee, we know that if it's unclear to us, it's very unclear to the observers. So we don't mind too much about that. However, if you want a long-term proposal, so something that would go over one semester, then you can apply for a longer project. And what that allows you to do is you put in your proposals, you can put in your proposal once a year, and then you get what's called pre-graded status, and you just have to submit kind of a here's what we've been doing, like a status update. And you don't have to go through that whole process of having your project reviewed again. So I had a long-term project, for example, that I only had to apply every second year. And again, it was just sort of a touching base thing. So there are different categories of proposals to kind of capture that. But when we're grading the proposals, we do kind of consider, oh, this is a lot of time for something that maybe isn't that earth-shattering. You know, we do make those kind of judgments. But again, since the telescope isn't greatly oversubscribed, like when we give a score for something, we're not then deciding, oh, well, we'll only give them half of that time. That really is at the discretion of the person who's doing the scheduling. So they'll look at what's available and they'll try to give priority to the higher scores. And again, that's a very, very widely varying function of galactic latitude. But yeah, I would love to help you out if you would like to propose some observations with parks. I have experience from proposal all the way to analysis and publication. So yeah, I'd be happy to help you out there.
Thank you very much. And thank you. Yeah, thank you for all the information.
All right. Is anyone else thinking of doing any kind of observations where maybe high sensitivity or big single dish or that kind of thing might be relevant?
And how about ATCA, Anita?
Etka. What do you mean? His subscription rate?
Yes.
Yeah, its subscription rate is higher than Parks. There's I would say that the ATCA gets more proposals for NAPA requests, which are those target of opportunity requests. So people put in a proposal and say, if we get something that triggers our observations, can we just hijack the telescope? So there's a lot of those kind of proposals, which they may never get scheduled if they never get triggered. So there's a lot of moving parts with the ATCA. But I would say that it's also true that if you control for the factor of the type of observations, that it is relatively undersubscribed for the type of spectral line stuff that we would be aiming for. But of course, with the ATCA, you're also tied to, because it has different configurations. So when they schedule it, it's a big beast to schedule. So there's a lot of constraints there, but yeah, it has a higher oversubscription rate than Parks. Beth?
I just wanted to speak about ATCA. So people might not be aware that there's a new correlator that's currently being commissioned for ATCA called BCAT. So I'm on one of the science commissioning teams. So I will be looking at, and Jay's online too, and Max has a slide on here. So we're on the high resolution spectral line team. So we're going to be looking at some hydroxyl for science commissioning. So that, I think it was open for shared risk in the last proposal round. But we haven't done our science commissioning just yet, so I don't know when that will be, but just to let people know that is coming online. And obviously as well, you can look at other spectral lines besides hydroxyl with that, and the correlator setup is meant to be very flexible. So yeah, I won't say much more about that, but just to let you know there's a new correlator that's coming.
Yeah, that's a really good point, actually, because with the ATCA, I think one of the big things that might prevent people from feeling very confident using it, like for example myself, because I've used it a lot, but I still wouldn't say that I'm very confident using it, is because with the old correlator, if anything broke, that's just too hard. So we're hoping that with this new correlator, it'll be a more stable system and a more user-friendly system. So we're really, really hoping for that. So yeah. And also, Beth, would you say that you're an expert on VLA observations?
I would say
I
that
think you're an
now.
expert on VLA observations.
Yeah. When I get to do my introductory slide, I can introduce myself properly. But I'm a PhD student, but I have a survey on the VLA that is, well, still observing. I get my emails saying that they're observing things. So I'm looking at H2 regions and molecular clouds. I'm giving a talk on Wednesday about that. But yeah, so we got 177 hours on the VLA. And there was also a pilot survey, which my supervisors, well, Joe Dawson, Anita's on it. I think a number of people on this call were on that proposal. So looked at 3 H2 regions with hydroxyl. So I processed that data, and there's a paper that's nearly ready for publication about it. And then I've got this bigger survey. So yes, I can definitely help with the VLA. I know there's a few other people like Michael Rugel, Trey Wenger, other people have experience with the VLA too. The trick with the VLA compared to say ATNF instruments, is you get to set up the correlator yourself, and it's very like customizable and choose your own adventure, which can be a bit challenging depending on what you're trying to do. But it's good in that way. You can set exactly the spectral resolution you want, the width of the spectral window, all that sort of thing. But yeah, so if you want help with some technical details of that, I'm definitely happy to help. But again, there are others who can help with that a bit more as well. Yes.
Can I ask something with the VLA? What's the product that comes to the observer with the VLA? Is it visibilities or is it images?
So there is a VLA pipeline. So it depends. I can request just the visibilities that come as a measurement set. And so then I could choose to do all the calibration and imaging myself. There is a pipeline that does calibration for you. And when you set up your observations, each scan, I'm assuming everyone knows about interferometry observations, but essentially you choose to point at your source, point at your calibrator, switch back depending on what you're doing. And you can say, this scan is looking at my science target, this scan is looking at my calibrator. And then those tags, I think, go into the pipeline so they know which is your calibrator, which is your science target, and then can calibrate from that. So I looked through the logs on some of the data that was calibrated, and it was like 16,000 lines of a log. And they do all the calibration steps. They do self-calibration, which I need to double check if that is good for our science data. So potentially, if you trust that calibration, you could go straight to imaging. They also do some imaging, but I think that's limited by, I don't know if it's like time that they can allocate or data that they can allocate. So they did do some imaging for me as well. So it just depends, I guess, on your science case, whether you're happy with their data products or you want to do it yourself. Just kind of the answer there.
Yeah, because that's an interesting distinction, because with the ATCA, you get the visibilities, and then you can process it in a way that that suits the science that you're trying to do. Whereas some of these bigger interferometers, I was just wondering where it fell on that divide, because I know the ASCAP, if no visibilities leave the site, because they kind of literally can't, because it's
Yeah.
like, what is it, like more than the whole world's internet traffic or something, some stupid statistic, which then of course leaves you in a bit of a mess, as Jay is very aware of. I'm hoping Jay will pipe in. I can see him. He's here. That, yeah, not having that ability to be able to process it yourself means that, yeah, you're kind of subject to somebody else's pipeline, and if that doesn't work for you, then that's a big old huge headache. But ASCAP is still in the sort of, we're figuring out the best way to do this stage, I believe, or at least that's where it was when I left CSIRO. But yeah, that's another thing to consider when you're trying to choose which telescopes you'd want to use. I'm not sure if ASCAP is even really open for anything other than these big surveys.
So there's a few things. So VLA kind of fits between, you get your measurement sets, you can do it yourself, or you can use their pipeline. I want to add as well with the VLA, before I mention ASCAP, they do the observing for you for the VLA. So it's not like ATNF where you do the observing yourself. They have observers with the VLA, and they send you a log, which is fascinating to see what happened. Apparently it snowed in February. I didn't know that. Didn't think of that as a thing. So I like that with the VLA. I don't have to do that 177 hours myself. With ASCAP, so there are the big survey science projects. So GasCap OH being relevant to hydroxyl, and Jo Dawson is one of the PIs, and I think she'll talk about that later in the week. You can also submit a proposal to do your own science case. So that is open for some hours during the semester. But I'm guessing if you're doing hydroxyl, they'll probably say wait for GasCap OH, depending. And I'm on the science commissioning team for that survey with Jay and Jo. And yeah, we're getting there. There's a big ASCAP soft pipeline. It's very complicated. There's a lot of knobs to turn. So we're trying to figure out the best way to get the data out the way that we need for our science case. But it is very technically challenging because the data volume is huge. Each data cube we're getting out is 2.5 terabytes. So it's massive. And in the end, when the survey's up and running, like Anita said, we're not going to get the visibilities. We'll just get the data products at the end. So you want to set it up so that the data products are most likely going to be satisfactory. But if we're not happy with them, they have to reobserve it, because they can't even keep the measurement set, like the visibility stored. It's too big, so they have to just dump it and then reobserve. So it's a challenge. I'm interested to see how this all works with the SKA going forward, but anyway.
Yeah, the SK is not keeping any visibilities. They're
Mm.
doing imaging. It sounds scary.
Yeah, they have the correlator on site, so that it can do all of the correlations on site, and then that information is sent via, I'm pretty sure, dedicated fiber optic cables to Perth. Which, if you know where ASCAP is and if you know where Perth is, that is pretty impressive because they're nowhere near each other. Yeah, the scale out there is huge. I'm glad you mentioned GasCap OH, because we're also going to have our session on Friday where we talk about sort of current and ongoing and future surveys, and we'll also have another similar list like this one with the telescope contacts of past surveys, current, ongoing, and future surveys, so that if you're interested in using the data or being involved in any kind of projects, then you'll know who to contact, because we have a lot of key people in this group. So if there aren't any other discussion points that people want to get to, it looks like we're right at time. Look at how good we've done. It's 10:58 by my clock, so good for us. So the idea is that we can keep the conversation going on Slack, and because we have a lot of people at this conference that aren't here right now, or at this workshop that aren't here, because there's a lot of time zone restrictions. So hopefully we can kind of keep that conversation going. Also, a recording of this session is going to be played at a later time slot as well. So if you're super keen to see the talks again, but have new discussion, then you can attend at that one. Otherwise, that's meant for people who couldn't attend this one. But that's going to be sort of the pattern of the rest of the workshop, is that we'll have some talks, hopefully spur some discussion, but then we're kind of open the floor and we can talk about anything. So thank you to our speakers, Allison and Michael. And thank you to everybody else who participated and everyone else who attended. Thank you very much. And I look forward to seeing you guys in the next session, which I think starts in like an hour, or maybe 2 hours. I can't. I'm flying by the seat of the program here. But thank you, everyone. And I'll catch you next time.
Thanks.
Thank you, everyone.
Thank you. Nice to meet you all.
Let's see, Anita.
Yeah.
Should we debrief for 1 minute?
Yeah.
Okay. So then we have, we could stop recording, right?
Yeah.
Okay, go. Okay, so then,
Is it still recording?
Oh, is
Only
it?
you is here.
I think only Heap or people pretending to be Heap can stop the recording.
Yeah, I will stop now.
Okay.